if it goes well, maybe I'll ask you for the recording.
Okay, I think it is being recorded. This is good. I think we can start right now, and then people can join during time. So, hello everyone. Thanks for joining our talk today. Our guest today is Professor Goyal from Boston University. He's a fellow of IEEE and Optica and co-founder of Foundation of Signal Processing. He and his students had numerous awarding conferences and from societies. Today he will be talking about subdual time resolution changes particle beam microscopy, and I think that the stage is yours.
Okay, yeah, thank you very much. I like that I can see at least a few faces, but so I appreciate that. Thanks to Amir for arranging the talk. I think we met for the first time at a workshop in fall 2019, and efforts to collaborate hit a worldwide pandemic roadblock, I guess. But you know what's funny? I at least that's the way I used to think about it. And recently I've started to think that the pandemic has made us all much more accustomed to remote interaction. And so we should actually just think that collaborating at a distance is now easier than it used to be. And I hope that this talk can spark some collaboration at a distance, even though I'm still not physically traveling all that much. So how sub-dwell time resolution changes particle beam microscopy? That's not my usual style of title, but I have that title because I'm trying to advocate for a specific concept, fine time resolution in particle beam microscopy, where conventionally there's no time resolution in this data. I'll tell you what I mean by no time resolution and the kind of time resolution I'm advocating. I think our idea has no significant traction yet, to be honest, but I believe that it can be significant. We introduced it about 3 years ago, and we have a sequence of works that develop various ramifications. So today I want to give you a high-level overview of our work and hints at some of the mathematical details that we found especially fun. So the title says particle beam microscopy, but to not get distracted by small differences, let's concentrate on helium-ion microscopes. Helium-ion microscopy achieves high resolution, surface sensitivity, and depth of focus relative to scanning electron microscopy. And these advantages are due to short wavelength and low interaction volume of helium ions. I'm quite sure, well, I don't know the full list of attendees here, but probably several of you are greater experts at these microscopes than I am. I'll just start with my novice's view of how a helium-ion microscope operates. So you'll understand my level of understanding and where my abstractions for the microscope are coming. So a helium-ion microscope has a helium-ion source and an electron detector. An incident ion causes emission of electrons, and the detected electrons are called secondary electrons because the source beam particles are called primary particles. Imaging is achieved by raster scanning of the beam with some fixed dwell time per pixel. The detected secondary electrons map to grayscale levels in the micrograph that's formed. So we're making an image of the propensity for secondary electrons to be emitted and detected at the different scan locations. One of the major limitations of helium-ion microscopy is that it's, and it's actually a limitation that's more important if you use even heavier ions, is damage. So it's important to keep the dose low. To illustrate damage, Shown here are images acquired with increasing imaging time from 52 seconds to 364 seconds, etc. So as the imaging time is increased, the shot noise is being reduced by the increased averaging, but the finer features are being destroyed by sputtering. Because of this, the ability to accurately image a sample is fundamentally limited. You can't just image longer to get a better image. And the more delicate the sample is, the more that's true. So since ion beam microscopy is limited by sample damage, it's important to make the most of any fixed ion dose, especially if it's a low dose. All right, so now let's make a statistical model. We look at the incident ions as a Poisson process, and each ion produces a burst of secondary electrons. In all of my illustrations, let's just assume I'm only showing the secondary electrons that are detected. I'm not including detection efficiency in this. Now, the number of incident ions, M, is a Poisson random variable because I've modeled the incidence of ions as a Poisson process. It has a parameter lambda. I'm going to call lambda the dose, and for now, I'm going to assume that it's known. And we model the number of secondary electrons per incident ion as also having a Poisson distribution, with each burst having a Poisson parameter eta. So that eta, that's the propensity to emit secondary electrons. That's what we want to learn about the sample, that value eta at each pixel. Now, to put some mathematical language around this, although I'm going to put aside the math for a good section of the opening of the talk, but a random variable associated with an arrival in a Poisson process can be called a mark. So our overall model here is of a Poisson-marked Poisson process. And we're observing in the full dwell time, conventionally, just the sum of the xi's, all of the detected secondary electrons. So that's what we're going to call y. And our goal is to estimate eta from y. Right? So that's our abstraction, applied separately at each pixel for now. Now, I want to have a little digression into fantasy to motivate why we believe there can be significant improvements over the status quo. The fantasy is to have an oracle that observes the ions, the incident particles. So now, under this fantasy, M, the number of incident ions, is known. Conventionally, lambda is known, not M. And so the conventional estimate is to divide y by lambda. With the oracle providing M, a better estimate is y over M. And the mean squared error with the oracle is dramatically lower. I'll give mathematical derivations and expressions later, but basically what we see is a difference between linear and quadratic dependence on the true value of eta. So that's a lot of room for improvement. Just to dwell on the graph for a second. So I'm showing the mean squared error in estimating eta. I'm not telling you what the dose level is for this particular graph. You know, it's to be notional here. And that mean squared error, it does depend on the true value eta. The horizontal axis is the true value of eta. And you see this great gap between what we get conventionally and what we could get with this oracle. So there's at least some hope of a very large potential gain if we can somehow do something that is similar to having that oracle. Okay, I'm still going to put aside, I'm going to push back the math a little bit longer. I want to just spend a couple minutes talking about what we could stand to gain in resolution improvement. So let's define resolution as the smallest feature that can be reliably determined to be present. That's slightly loose definition, but I'll give one possible interpretation of that in a second. So suppose that what I've shown on this graph is one line of a micrograph plotted as a function of position. A single short scan might give a result that's not easily interpretable. Right? There's noise at every pixel, and it isn't clear whether one should think there really is this dip feature present at around position 250. There's a second acquisition, just a second pseudo-random Monte Carlo trial, different realization of noise, and again, it's not clear whether to believe there is a feature present. Those acquisition doses are probably too low for reliable results. Over a little bit longer acquisition, we could compute the mean and the standard deviation for each pixel, and we could declare that non-overlapping error bars. So here our error bars are standard deviation. You could say, I want my decisions to be more reliable than that, so I use, 3 times the standard deviation or something like that. But just qualitatively, to see the improvement, I'm making error bars that are of the standard deviation. And then we can define resolution as the smallest feature that gives non-overlapping error bars. Okay, so let's see what we get out of this. So here on the left, error bars are too large for confidence that there really is a dip present. And on the right, they're small enough for being confident that there really is that feature present. All right. So let's compare what we can get with conventional processing versus what we can achieve with some kind of improved processing. Here, the size of the feature is 50. On the left, we have the mean and the error bars for the standard method. The error bars don't overlap, so I put a green check mark to say that we'd be confident that a feature is present. On the right, we have the mean and the error bars for an improved method. Both methods are unbiased, so the blue curves are the same, but the error bars are smaller with the improved method, and we'd be confident that the feature is present. Now we reduce the feature size from 50 to 45. The error bars are larger, but both methods still succeed. We reduce the feature size again to 40, and now the conventional method fails in the sense that the error bars are overlapping, whereas the improved method still reliably distinguishes the feature. At 30, the improved method is still successful. At 25, it again is successful. At 22, it's just barely successful. At a feature size of 20, now even the improved method is failing by this metric. So my claim or interpretation of this set of simulations is that the resolution has been improved from about 45 to about 22. So this is how I want to tie a reduction in mean squared error or a reduction in variance, if all the estimators are unbiased, to an improvement in resolution. Now let's get into how, some of the details behind why I believe this is possible. All right, so I'm going to now add in some mathematical modeling and analysis. All right, so remember that y was my name for the random variable that is the total number of detected secondary electrons in the dwell time. From the abstraction that I showed you, that random variable y, it's a mixture of Poisson random variables. This particular likelihood function has a name. It's a Niemann type A likelihood. It's not the easiest thing to work with, but you can easily show that the expected value of y is lambda times eta. Because of that, a simple estimate of y over lambda is an unbiased estimate of eta. And conventionally, people may not even be thinking of the problem as a quantitative estimation of eta. You're just trying to form an image of how y varies from pixel to pixel, And in fact, because of this unbiasedness, making an image of y is really a reasonable way to look at how eta is varying, if you don't care about the scale. The variance of y is lambda eta times eta plus 1. Because of that, the conventional estimate of y over lambda has a mean squared error as shown there. It makes sense that it's inversely proportional to lambda. As you increase the dose, you're really allowing yourself to average over more observations. But remember that if you increase lambda too much, you're going to blast away the features that you're trying to image. So I don't want to think about reducing MSE by increasing lambda. I just want to consider lambda to be fixed, given to me by the dose limits, basically how fragile the sample is. And for whatever fixed lambda there is, I want to have the lowest MSE possible. Now, if the beam was not a Poisson distributed number of incident ions, but instead it was deterministically exactly lambda ions, then the variance of y would be lower. It would just be lambda times eta instead of lambda times eta times eta plus 1. So this factor of eta plus 1, it's the price of having a random beam, which we sometimes call the source shot noise. And we want to not have to put up with this extra factor of eta plus 1. Could also say that extra factor of eta plus 1 was the difference between the linear and quadratic curves that I gave you in that earlier preview. Our key idea is to introduce time resolution. So this time resolution has nothing to do with a phenomenon usually associated with time. We're not measuring time of flight, and we're not looking at the dynamics of the sample. That would be an additional complication. So I'm just thinking the sample itself is static, but we're using time resolution only to improve our ability to estimate eta. Here I'm changing the style of illustration a little bit. This is emphasizing that in our abstraction, the secondary electron bursts from any one incident ion are approximated as simultaneous. So now here is an example of a rate lambda Poisson process for the arrival times. And then the height here, the mark, is a Poisson distributed random variable. Now, this process, which was my fundamental abstraction of how one of these microscopes works, this is fundamentally, whoops. I accidentally clicked. Okay, so that is fundamentally unobservable. I mean, what I mean by that is because we're only detecting secondary electrons, we can't know the times when an ion was incident, but there were 0 SEs, right? So these 0 marks make this unobservable. And remember that, conventionally we observe just this total, a single scalar, just the total number of SEs. Okay, because we can't observe the arrivals that have a mark value of 0, there's a thinned Poisson process that is in some sense observable. At least, if I had fast enough time resolution at a detector, this is in principle somehow observable. And this is what we call our continuous time model. Now, the arrivals in the original Poisson process were rate lambda. This thinned process has a little bit lower arrival rate. It has that factor 1 minus e to the minus eta. And the marks, well, they used to be Poisson distributed, but now we've truncated that Poisson distribution by throwing out zeros because we can't observe those. Finite time resolution creates some number n of time slots. That's our definition of bringing discrete time resolution into this. And totaling each sub-acquisition gives then one scalar per sub-acquisition, and that's what we call our discrete time model. Now, it turns out, like, in terms of the history of our work here, we started only analyzing this discrete time model, and it only occurred to us later to attempt to analyze the continuous time limit. And the continuous time limit is just mathematically so much simpler. So I'm mostly going to talk about the continuous time version because I can give you some simple intuitions really quickly from the continuous time version, and the papers actually describe the discrete time model in more detail, and we even give mathematical proofs of certain n to infinity limits of the discrete time results converging to the continuous time results. All right, so the continuous time model, it essentially, oh, I see it. You know what? I haven't been looking at the chat. Amir, why don't I ask you to interrupt me if I should see something in the chat? It's hard to actually look at the chat.
Sure. I will look at it.
So I'm just going to trust your judgment on whether whatever that is in the chat is a question I should try to answer now. All right. So this continuous time model that we have, it reduces to knowing m tilde, that's the thinned, the arrivals in the thinned process, and knowing the total number of secondary electrons, y. I mean, when I say reduces to that, for the purpose of estimating eta, I should have put it this way, sorry. For the purpose of estimating eta, y and m tilde have all of the information, because conditioned on knowing m tilde, there's no information about eta in the arrival times. That's one of those basic properties of Poisson processes that we've seen. So I'm just trying to estimate eta as well as I can from y and m tilde. The discrete time model is that n tuple of Niemann type A random variables, where before we had parameters eta and lambda. Now we have eta and lambda over n, because the full dose of lambda has been divided into n smaller doses of lambda over n. But like I said, I'm going to mostly concentrate on the continuous time model here. It's much easier to analyze, and it matches the n to infinity limits in certain ways. Okay, so one of the ways to understand the advantage provided by the time resolved sensing, and it also illustrates the elegance of the continuous time analysis, especially if you first read our discrete time analysis and how messy it is through Fisher information. So we're interested in the Fisher information about the parameter eta that's present in the measurement y, or in y and m tilde, in whatever we have available to us. So how does this Fisher information behave when it's normalized by lambda? So this graph, it's a non-trivial numerical computation because of the infinite series in the Niemann type A likelihood function, and deriving those asymptotes that are marked there. I mean, it's also, I can call it non-trivial. It's a mathematical fun. It was definitely a fun part of this project to derive those asymptotes. The Fisher information for a continuous time observation turns out to exactly match the upper asymptote of this plot. That's another bit of fun math. So this is telling us, so first of all, before talking about the asymptotes, what is the blue curve here telling us? It's telling us that to have the best normalized informativeness, or informativeness per unit of damage to the sample, it's best to have very low lambda measurements. And Fisher information is additive over independent trials. So this plot we can use as a justification for taking whatever dose is available to us and always divide it into smaller doses and repeat the measurement. Right? So if I had let's say that the sample can withstand a dose of lambda equals 10, right? So I'm pointing to maybe I should have marked this on the graph, but I'm pointing to around lambda equals 10 here. And what this graph is telling me is that if I instead use 100 sub-acquisitions so instead of operating here, I could have 100 sub-acquisitions here, and I'd have this substantial improvement in the informativeness of my measurements. Okay. So it's basically telling us that continuous time measurement is good because as I go to the left, I get more and more improvement. This graph is also telling us that there are diminishing returns in making the time resolution finer and finer. And that's reassuring as well. Like if it turned out that I needed, extraordinarily fine time resolution to get any of the advantages that I'm claiming, well, then this would be less valuable. But it seems that, if I keep, let's say, the dose per sub-acquisition at 0.1, then for whatever total dose is appropriate based on how fragile my sample is, I'm getting most of the advantage of the continuous time or the time resolved sensing. Sorry. Okay. Now, if I look at those asymptotes, the factor that separates them, that's the improvement factor that I can hope to get from time resolved sensing. And that improvement factor is pretty similar to the eta plus 1 factor that we saw as being the price of source shot noise. All right, so now let's look at estimators computed from the continuous time observations. As I said before, in the continuous time setting, m tilde and y contains all of the information because conditioned on m tilde and y, there's no additional information about eta in the arrival times or the individual x tilde i's. Earlier, I introduced the idea of an oracle that tells us the number of incident ions m, in which case y over m is a great estimate of eta. We could just use m tilde as a proxy for m. We call the resulting estimator the quotient mode because it's a simple quotient of observed quantities. And Zeiss used the same name for a similar concept. So then we would estimate eta as y over m tilde. All right. When we use m tilde as a proxy for the number of incident ions, this is actually ignoring that thinning that is caused by ions that induce zero SEs. So we could instead use the adjusted quantity shown here, except that it's an adjustment that itself depends on eta. So you end up with an equation to solve, and the solution of that equation involves the Lambert W function. So we call the resulting estimator the Lambert quotient mode estimator. A statistically principled thing to do is to compute a maximum likelihood estimate. This turns out to be the unique root of the equation given here. And it turns out also that instead of going through the derivation of the ML estimate, if you instead think about computing the minimum mean squared error estimate of m and plug that in, you get the same result. So we have a few different estimators that use this additional information from continuous time measurement. And here's a comparison of those estimators by Monte Carlo simulation. Conventional is to divide y by lambda. The oracle is to divide y by the unobservable m, right? So we can't really implement that oracle. We can see that the conceptually trivial quotient mode estimator isn't good at low eta, but it's actually quite good at higher eta. And the potential improvement from these more sophisticated estimators is huge. And we've basically, we've realized almost all of that gain that I was hoping to be able to realize, the gain between the conventional and the oracle. I should say that electron microscopy has low eta, like between, say, 0.2 and 1. So unfortunately, we don't get big improvement there. But for helium ion, for the helium ion range, or for heavier ions, the improvement is indeed quite large. So now, I don't want to show you simulations of exactly what I've shown so far, because those would be simulations doomed to succeed. They're not going to be very interesting. I'm going to show a glimpse of some preliminary experimental results. And I confess that I'm leaving out a lot here between the continuous time theory, which I wanted to include because I think it's relatively understandable even without a lot of detail, and these initial results, right? So everything I've been describing so far is based on direct detection of SEs, but the data that we had available to us is for a Zeiss Orion NanoFab HIM, which does not have direct detection of secondary electrons. So I'm leaving out a lot here. It's described in that ultramicroscopy paper. John Noddy of Zeiss provided us with time-resolved data to test our ideas. And what I mean by that is we had a 0.1 picoamp beam current, and for each pixel collected a large number of sub-acquisitions that are 200 nanoseconds each, right? So we could use different subsets of those sub-acquisitions to get performance, get performance at various different total dose levels. We also had to use the same data set to get some kind of a proxy for ground truth in order to have some kind of a mean squared error estimate. So there's a lot I could say about exactly how we do the data processing and how we claim to have estimates of mean squared error. So we have a hat on the MSE there because these are estimates of mean squared error based on producing a proxy for ground truth that combines multiple image formation methods. But the bottom line is that at very low doses, we demonstrated an improvement by in the MSE by a factor of 4, which is even more than what our idealized simulations would have predicted based on what we believe the SE yield for this sample is. There's a lot omitted here. Some of it's included in that ultramicroscopy paper, and some of it's kind of ongoing work. But instead of explaining this more, I just want to use the last few minutes to give some hints at some other results. Just talk about some other directions we're going. So this last part is on mitigating beam current fluctuation. Particle beam microscopes, as I understand them, can suffer from beam current fluctuations, especially associated with contamination and aging. In a gas field ion source specifically, the source ions are coming from a triplet of atoms at the tip called the trimer, and the maintenance is called baking the trimer. That takes the instrument offline for a while, which is expensive, and that exhausts my materials knowledge. But for our purposes, let's just say that electron and helium ion beams can have continuous fluctuations in beam current, and neon ion beams can have discrete jumps in beam current. Again, I don't want to overstate my expertise in the slightest, but my understanding is that the lack of stability of the beam current is a major reason for the slow adoption of neon ion beams. That a neon ion beam will tend to jump between a few discrete stable states, and that creates some kind of a flicker. So the illustrations here are Monte Carlo simulations, but they're to illustrate the type of artifacts that come from beam current variations. There are existing techniques to try to reduce these artifacts, but those techniques, they're all basically post facto image processing. They're the removal of these horizontal stripes without physical modeling. And what we have attacked is to be able to compensate for the beam current variation by literally estimating it from plausibly observable quantities. We really want to use just the same data to form the images and estimate the beam current. So our modeling, our physics-based probabilistic modeling, shows that the beam current lambda and the SE yield eta can be estimated from the same data when that data is time resolved in the sense that I've been discussing here. If we didn't have time resolved data, this would be like I have one scalar value per pixel, and I somehow want to get both lambda and eta at that one pixel. It would be like estimating both factors of a product from one number, which sounds extremely hard. Maybe it's possible because of correlation of pixels, et cetera, et cetera. But so I don't want to claim that kind of crazy magic. It's not that, but because we have time resolved data at each pixel, it actually becomes plausible. And the paper that's cited there at the bottom includes Fisher information analyses and various kinds of simulations to demonstrate this. So having a vector of data per pixel creates this new capability. Now, on this slide, I'm presenting one example each for continuous and discrete beam current variation. In both of these cases, the joint estimation of lambda and eta can give performance that's almost as good as if an oracle was providing the beam current. So the conventional estimate here means you're basically ignoring the fact that lambda is varying, and you just get stripes. My use of oracle here is to suppose that the varying beam current is known and that we apply the ML estimator of a few slides ago. And what we found is that a joint estimation, which depends on assuming that the varying beam current follows a Gaussian AR1 process, can come extremely close to doing as well as if you have the oracle. And we also develop algorithms to do that joint estimation of lambda and eta, but also use TV regularization for the image data, use TV regularization for eta. and then we get even better results. On the bottom, it's a similar type of example, but here, inspired by a neon ion beam, the variation of the beam current is discrete. And again, so here, a hidden Markov chain estimation method is appropriate, and the joint estimation again comes extremely close, essentially matches the performances of having an oracle. Now, here I've emphasized that you can get a better micrograph, but the estimation of the beam current could be viewed as some kind of a new online diagnostic for the instrument. Okay, and just to give you one small bit of just a mathematical observation. So part of the fun math that came in doing this work was to deal with the derivatives of the log likelihood, where, remember, the likelihood is itself this ugly infinite series. And we showed that the derivatives of the log likelihood of a Niemann type A distribution, that is, the derivatives both respect to lambda and eta, can be written using two-sharp polynomials. And we exploit that in the numerical algorithms that are presented. And in fact, it was a little fun part of the project. And one of the reviewers of the TCI paper might have appreciated it even more than we did, because a reviewer pointed out that this Niemann type A distribution arises in various other problems where it might be useful to be able to take derivatives of its log likelihood. All right, so to wrap up, time resolution finer than the pixel dwell time, I am claiming to change particle beam microscopy substantially. The MSE for estimating eta, the secondary electron yield, can be lowered roughly by a factor of eta, and this is uniformly across lambda. It's not a result that's depending on the beam current. When we started this project, I thought we might only get interesting results for low lambda, but the results are actually uniform across lambda. That same improvement, I mean, instead of thinking of it as a reduction of the MSE, if I'm willing to have the same MSE, I could lower the dose roughly by a factor of eta. I showed how this could be interpreted as leading to an improvement in spatial resolution. I showed that we can mitigate beam current variations in terms of improving the image quality, and that might be also enabling some kind of an online diagnostic of the instrument. I hope there's a lot more that we can do along these lines. I'll tell you right away that a lot of what I omitted here was the gap between this relatively elegant model that has direct detection of secondary electrons versus existing instruments that do not have that direct detection. So there's a lot of additional noise in the measurement process that we modeled in certain ways for that ultramicroscopy paper, but I think that's not completely satisfactory. And yeah, so it's a continuing line of work. If this sort of work seems fun, we have openings for students and postdocs. Of course, I know I'm not speaking at a university right now, so but you still may know people who are interested. If you do, encourage them to get in touch. At my webpage, you'd find a link to the group's YouTube channel and more. So I'll wrap it up there. I hope you have questions. I hope I sparked some thoughts. And of course, I'd be happy to get into more of the mathematical details. I hope I hit the right level of inspiring you to want to know more.
Thank you very much for your talk. So let's see if there is a question from the audience. Yeah, go ahead, Venkat.
Okay. Hey, Vivek, great talk.
Thank you.
Very, very interesting. So maybe the first part is not a question. I just wanted to make sure I was like getting, the high level, I mean, the big picture again properly, is that if you have like systems where there's a reasonably large count, it looks like having a faster detector. So the trade-off in some ways is to be able to build these detection systems which are faster than. So I'm guessing that in the conventional approach, I've not worked with helium ion. They might be they might be having a certain detect a rate, right? So it sounds like by going to faster detectors, we can improve. We can have lower dose imaging. Is that by using all the
Yeah. I think that I agree. I mean, that's a good summary of the take-home message, that if the detectors are fast enough. Well, what does fast enough mean here? Fast enough is to be able to distinguish the bursts of secondary electrons per incident ion, instead of only seeing those bursts of secondary electrons after they've been added together. So if I'm only seeing those secondary electrons after they've been accumulated across multiple incident ions, then I see some number of SEs. It could be because of 3 incident ions. It could be because of 4 incident ions, let's say. And I mean, it could be wider than that, but let's just say 3 and 4. I mean, just the uncertainty between 3 and 4 is already a lot of uncertainty if notionally that ought to be in the denominator of an estimator. Right? It's like 33% error right there, just because I don't know whether it was 3 or 4 incident ions that created this signal.
Okay, great. So and one follow-up, and I have a question after that, is that so we need so it sound I mean you mentioned this and I probably missed so you need to have some estimator for the number of incident ions, right? So is that something you derive from the beam current? Is there some heuristics that we can use maybe to?
So I'm getting that number of incident ions from kind of burst counting.
Okay.
Obviously, with anything like this, I had various versions of these illustrations, and maybe, there's a different version of these illustrations that I should have emphasized. But let me just go all the way back to, my first illustration. I think it's worth it. Oops. How much I added. So all the way back to this, if my time resolution is good enough that I can kind of see these bursts, then I'm going to be able to know exactly what M is, or at least, sorry, I shouldn't say know exactly what M is, but that's actually, it's knowing what M tilde is, what I've called M tilde, that thinned process. So the difference between our continuous time model and our discrete time model is that we include all the details on how the coarseness of the time resolution lets you, well, it affects how well you can estimate M tilde itself. If my time resolution is very fine, then every time I see a non-zero number of SEs, I treat that as an incident ion.
Okay. Yeah. Perfect. Thank you very much. That was great. I think and so now the question was, is like, so in these, again, not having worked with helium ion, but a lot of times like they talk about like some kind of deconvolution, right? So spatially, these ions hit, and then there's like I'm guessing some kind of like interaction, and there's an interaction volume. So when we move from one pixel to the other, there is some kind of a correlation between, I guess, the etas like that are like next to. There's some kind of like, yeah, I'm not sure I'm framing it right, but there's some kind of spatial convolution of some.
Yes, yes.
Did you?
You're absolutely right. And actually, that's another thing that I didn't include that style of discussion here. So so for almost everything I said here today, my mental model is so simple that each raster scan location just has an eta value associated with it, and I'm not concerning myself with how that eta value is related to the the width of the beam or the underlying sample. The one exception is that actually this resolution analysis that I went through, it's actually simulated based on a Gaussian beam spatial cross section. So I didn't, again, I didn't talk about this very much, but what's happening as we vary the size of the feature in this sequence of Monte Carlo experiments is the feature is eventually becoming relatively small compared to the cross section of the beam, and then because and again, our mathematical model is that we have a convolution, like you said, and so as I make the feature size smaller, the notice that the mean, the mean at the trough is actually increasing. And that's because as I'm making the feature size smaller, more of the neighboring non-feature parts of the profile are being convolved in, right? And that's part of why we stop being able to distinguish the feature, right? So that's what I dropped in these slides that are extremely preliminary. A great postdoc of mine who just started like 6 weeks ago made these slides to try to connect the concept of MSE to the concept of resolution. But this is very preliminary, and we're really trying to quantify this now much better.
Great, thank you. And I really like this. This was like, I really love these the MSE and the feature size. I've not seen. It's great. Thank you for that.
Yeah, thank you.
Thank you very much. So do we have any other questions? So I think we don't have any other questions. So for me, actually, so other than helium ion FIB, where else do you see application for this? Because we have tried previously the SEM, at least some of them, and so you mentioned there are problems with the SEM for this application. Where else you can apply this?
Actually, so first I want to comment on the applicability to SEM. Oh. So another one of the pleasant surprises of this work was that the joint estimation of beam current and image, it somehow is effective even when eta is relatively small. So it seems like now we still have 0 real physical experiments to back up this joint estimation part. I mean, this is purely theory, algorithms, Monte Carlo simulation. But this part, it somehow is giving advantages even at low eta values, whereas the earlier work that was just about low MSE estimates when lambda is known, there the advantages disappear when eta is too small. So that's one comment. I'm not giving up on SEM because there may be ways to add value in SEM. And I guess I don't have very concrete answers, but I'm trying to think about optical problems that can have similar distributions arise. You know, there's like multiphoton microscopy also has, in some sense, relatively small numbers of incident particles, or at least the coincidence from the two sources in two-photon microscopy, the coincidences are relatively rare. And I'm curious whether we can extend any of our modeling to add some kind of value in multiphoton microscopy. And well, we don't want to give up on ion beam microscopy either.
Yeah.